Hello developers, let's start developing. My name is Veko and tonight we're gonna be going through the 23rd task of the Advent of Code 2021, which is the Antepelm Ultimate one. I actually already wrote some code that I thought I was recording, but somebody didn't press the button and that's why we're doing it. So the task itself, we have some terribly specific input. And these represent some kind of weird shrimps or amphipods or whatever that we need to move them in a specific way so that they get to their room of their choice. So we have 4 side rooms, A, B, C and D, and those 4 side rooms, the A side room needs to contain A's, the B side room needs to contain B's, the C side room C's, the D side room D's. And that's the problem. So this is a terribly, so to say, unique problem. I don't think that we can reuse any code that we're going to write for this for any other problem, because if this is even slightly different, the task will be immensely different. So it's not that we don't have some kind of we will the solution, whatever solution we come up, it's not going to be reusable, it's not going to be extensible, it's going to be hard-coded. So that means that I can basically also hard-code what I want. So in order to move everything, we have some complicated rules how they can move. And basically it means that we cannot move on these fields 2, 4, 6 and 8. We can move over them, we cannot stand on them. Each move, we cannot have a move that goes from a corridor to a corridor, to the position in the corridor. We cannot have a move that goes from a room or a corridor to the room which is not the destination room. Which means that if we have a shrimp A of type A, this shrimp can go to the corridor or it can go to the A side room. It cannot go to the other side rooms. And once it is in the corridor, it won't go to if we move this A1 to this position, it cannot go to the 7th position afterwards. It can only go to one of these positions. And those are the only valid moves for it. So that's the situation that we have. So what I started to do, I decided that I'm not gonna parse the input, I'm gonna hard code it. This is the format of the input, basically a tuple of 4 elements, each of which is a tuple of pods. And I tried to generate an extremely long and convoluted barrow paths, to basically to enumerate all the different barrow paths that we can have. It is hard-coded, but so what? We also implemented a method that is called canMove that kinda adheres to those rules. So let's go through it. So we have a from to to. If the from and to are the same, we cannot move because it doesn't make any sense. If the from is empty, we cannot move because there's nothing to move. If the to is not empty, we cannot move because we're moving on top of something. So we're getting the actual pod, we're checking whether we are moving to a side room, if the to destination starts with A, B, C or D. So if we're moving to a side room, it needs to be the correct side room because we cannot move to an incorrect side room. But we also cannot move to an incorrect side room if there's already a pod there that's not of our type. So we cannot move. If this D moves away here, now it cannot return to this side room until C2 leaves. And if we're in the corridor, if we are moving to an end, we are moving to the corridor. So if we are moving from the corridor, that's not valid. Or we are moving to an entrance of the rooms, 2, 4, 6 and 8, that's also not valid. And now we needed to implement collision detection, and in order to implement collision detection, what I wanted to do is basically enumerate all the possible combinations that the movements can do. So the moving itself, the collision detection itself will be completely trivial, because if we are moving from position 3 to C1, when we are moving through these positions, are they available? If they're not available, the move is invalid. If they're available, the move is valid. That's it. We were only left with, I guess, 64 more values, because we need to see how we can move from a room to a room. Actually, this should not be. This is an array of an array of an array. It's not an array of an array of an array. It's something like this. And the last one is an array. So we are wrong. This is an object and 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 an object. So this is not a push. This is this. Yep. Because from going from A1 to index, we are moving the exact same part as we are going the other way around. So I did it once, and now I'm just copying them instead of making an absolute mess. And of course, it's not that this doesn't look like a huge hard-coded mess, but sometimes huge hard-coded messes are not a problem, especially if they work. So what we're missing, well, we're missing kind of this. How do we move from one room to another? Only instead of 0, we need to have A1. Yeah. So this will be an empty array from A1 to A2. It's the direct movement, it's an empty array, and this is 2, 3, 4, 2, 3, 4. And this is 2, 3, 4, B1, and this is 2, 3, 4, 5, 6. Well, yeah. So moving from anything, this is same like moving from 1 to all of those. Only for we will need to replace this with A2. And we will need to add that we need to go through A1 first. No! I copied the wrong thing. A1 and 2 first, because I wanted to copy the movement from 1 and I copied the movement from 2. Did I? Yeah, from 2 we're starting from 3, from 1 we're starting from 2. So we need to paste in these. yeah, this will take some while, so I will pause it for now and come back when this is done. And we can continue. We have right now a burrow paths object that basically contains all the paths through a burrow in something that is just 200 lines of code. Yeah. Hopefully we don't have a bug in this part. If we have, it's gonna take a while to find it. But one way to find out. So now we have all that we have, and we need to do the collision detection. So for the collision detection, basically we need to get the burrow paths of from to, and that's the path that we're gonna take. And path dot filter, let's filter each part of the path where path doesn't equal a is a room. A room is, oh yeah, we have the rooms. So for each room we have to get the occupancy of that room, and we call that burrow. Yeah, let's get the burrow of that room, and we're gonna get a pod. So that means that is that pod equal to the empty pod. Basically every path should be equal to that. And or we can write it inversely. If some part of the path is not equal to that, yep, we're gonna need to return false. So in order to execute the move, we're gonna need the exact same thing. As the so we need to get the pod. The pod is burrow of from. We need to set the from. So how long is the path? Let's ignore the price right now. We can get the price, but let's just see if we can move it, and the moving is itself is trivial. Basically, burrow of from should become empty, and burrow of to should become pod. And let's take care of the price as well. So the price will be always the length of the path plus 1. What is the type of the pod? Well, we can get that from the pod dot 0. And we can have a constant with the prices, and that can be basically A1 is 1. It's not gonna be like this, but it's okay. So A is 1, B is 10, C is 100, and D is 1000. That's okay. So we are getting the type, the price is prices of type, the pod is actually a capital letter. And actually we can change this. If can move from to borrow, then we do this, and return price success true, otherwise return success false, as that is an invalid move. So let's see what happens if we try to simulate the moves that we already know. That's the starting configuration. So basically what is happening, 0, 1, 2, 3. We are moving C1 to 3. And using occupancy. Let's see what the occupancy is after we execute that move. So C1 is empty, and B is over there, so that was a successful move. Let's do this. From C1 to 3, and then we are moving B1 to C1, oops, sorry, lost it somewhere. So I'm just trying now to execute the scenario that we know is okay, and then a desert antipode moves out of the way. So we're moving B1 to 5. No, B2 to 5. And then we're moving 3 to B2. And that's this part. The leftmost bronze antipode moves to its room using 40 energy. So yes, from A1 to B1. Both outputs in the rightmost move into the hallway. So the D moves to, what is that, 7, D1 to 7, and D2 to 9. Both desert antifoot move in the rightmost room using 7000 energy. So now we have that this one should go to, so 7 goes to D2, 5 goes to D1. And then we have, yeah, this is this case, and then of course 9 goes to A1. Let's try that. For each for off, move off moves, price success, execute move, move from, move to. What's the problem? No, move is an array of from, which is a room, and to, which is a room, an array of those. So that's okay, and we're just gonna log the success. Zero. And total price. This is just gonna be let and let's see if this somehow makes sense. True. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 moves went okay. The seventh one we messed up. 1, 2, 3, 4, 5, 6, 7. Yeah, this is D2. Goes to 9. That's the A before below the D. So we got A, B, B, C, C, D, D, and everything below above that is fixed. And now what will we say if so basically what we need is the borough to be equal to the target. Just a sec, let me check what to array of borough will return. Yeah, well, actually we can use foreign, and we don't even use that. Exactly. So we can just compare whether our borough actually equals to the target. Yeah, let's do that as well. It's complete, and it says that the total result is 4132, which is wrong because the price is wrong. That's the price. We don't need to return the price. We return the price times the length of the path. Burrow paths of from to length plus 1, because we need to add 1. And that's the price for the move itself. So it says 12, 15, 21. And the total move would be, no, this is the minimum energy to do that. Okay, so we have a somewhat, let's call it, stable way to execute a path. So if we are given a path, we can execute that path and determine whether it's complete. But how do we actually execute, get all paths? Well, let's be wasteful. Yeah, I will just comment this out for now. And this we don't need. And the occupancy is, yeah, it's a constant. That's the input. So let's generate all the valid moves. Let's see how many there are in the first place. So, the key is a string. The key is not a string actually. Actually, this is something like this. Key in room and the result is pod. So now the element, we are getting that it's any, and there's actually the whole hoopla, but can we annotate this? No, we cannot. Yeah, we're getting that the key is a string because in general we just cannot guarantee that we don't have a monkey patched occupancy. In this case I know that it is because I'm declaring it just above, but in general we just cannot. So what will we do? What will we do? For each key, let's get the pod. And this is not the cat key, this is a room. We're getting the pod. And the pod is, yeah, a pod. If the pod is empty, just continue. We cannot move an empty space. Technically we can also call can move, but meh. Let's optimize it at least that much. So if we get the pod, how do we get all the rooms? And we actually had that. Let's do a little bit of it's, yeah, we need this, copy and redo. Yeah, we're gonna bring back the rooms, because in that case we can say if can move from, oh, this is not a room, this is a from room, and this is a to room. Yep. And we have a pod, this kind of pod in that room. So let's, for unoccupancy, let's see what are all the valid keys, valid moves. And it says we are missing something. 418. Okay, that was stupid. We're just not returning anything from the first part, from the part 1 method. So let's see, we can move this B to 01357910. We can move that C to 01357910. Yeah, those are the valid moves. So basically we have a series of 40 valid first moves. Let's refactor this to a method. Let's refactor this to a method manually. For a given borough. So this is not that. And the rooms we can move here if we don't need them. And this is a borough. And we need to return a room array. So yep, that's the result. So if can move, we can just add it. Let's be nice. From room to room. So this is an object and not an array. Let's just call this from, and let's just call this to, and then we can just return that. And of course return result. So if we have a barrel, a given barrel, we are getting all the valid moves for the next thing. So now we can have a very inefficient implementation of this. We can have situation like const next get next moves for that occupancy, for of move of nexts, Okay, now we have a bit of a problem, because we cannot run this in parallel. One of our functions is not pure, and that one is execute moves. Just a sec, I will remove this, since we kinda refactored it, that we are always assuming that this will work. Yep. But we are getting one barrow and we are returning the same barrow. We will need to do something like this. Nope, that's not gonna work. This will. Equals barrow of key. And we're just gonna say we are always returning a barrow. And this is a barrow, even if it doesn't know it. So we're not gonna use that, we're gonna use this and this and this, and gonna return a barrow as well. So what do? We are getting the next move, and for each of the next move we do something like this. Get all the possible next moves. So we have all the possible next moves, and then we basically need to generate the next possible values. Let me think on this a bit. I'll be back. Let's continue after we do. So basically what we want to do, we want to have a method where we will give it the occupancy and it will return to us the maximum price, the minimum price that we need to pay. for a given occupancy. Yep. And that's all we need, and just we're just gonna return you the price. One slight problem, we don't have such a method. Well, that's gonna take a borrow, not gonna take a list of moves, and it's gonna return a number, and let's say it returns a 0. So, how do we get the minimum price? Well, it's simple, so to say. The minimum price of a given occupancy is actually the minimum price of the all of the next moves. Yeah, so we're getting the next borrow. If we execute the move, if the borrow is complete, we'll need to return the price, because that's the price, that's a single move. Otherwise, we need to return, or we are not returning, min price is number dot infinity, positive infinity, let's call it, else the total price of this borrow is this, the current price plus the minimal price of the next one that we got. And if that price is less than the minimum price is equal to the total price. And I have a feeling that here we could do some kind of heuristic trimming. Basically that even before we execute the move and execute the step, we can somehow evaluate whether this thing is possible. Because, for example, if we have two D's that are here, then the minimum, theoretically minimal price will be 1, 2, 3, 4, 5, 6, 7, 7 and 8, 15,000, with 3, 21,000, 18,000, something like that. So basically this D needs to get to there, and everything else is clear absolutely. Then the minimum price would be 1, 2, 3, 4, 5, 6, 7, 8, 9, yeah, 19,000. So if 19,000 will be over the minimum price, we don't need to recurse, because whatever we do, we're gonna go over it. But for now, let's just see if this will actually return anyway. And I will just do something like this. If this will get done in an hour or in a second. Actually, yeah, this is too much. Let's see if we manage to complete anything. let's run it here. Oop. And we got an error because of maximum call stack size. How do we do this? Well, let's memorize it, because there are lots and lots of options, but basically a given burrow can be created into a string. Let's create a key out of the burrow, and this is not gonna work, but actually it will, because the keys. Okay, we can do this, and we're gonna do result push key burrow.key. I think there's a smaller format. Join with a dash. Let's just take a look at few of those. Console log to key of burrow. Zero B, one dash. Yeah, the dash is not a nice separator, so let's change that to a pipe, because we're already using the dash for something else. Oh, yep, and this is exactly what I was afraid of. We are basically doing an infinite descent on the first move. So basically we have a legal move, where the first legal move in this scenario is moving A to position 1, and the first legal move in this scenario is moving A from position 1 to A1. So we keep going back and forth, back and forth, back and forth. So we need to make sure that in any sequence of moves, basically we don't have a loop, such a loop, because if we do have a loop, then any solution with a loop is more expensive than the same solution without a loop. But how do we disallow loops? We can keep a array of moves as part of the barrel. Yeah, let's do that. Yeah, and that's a string array, and that's gonna be initialized on the empty array, and we can just say, what can we say? Well, const move of next, if moves dot in Um, Move key will basically take a move and suggestion. Yeah, no. Yep. Move from, and actually I'm not gonna put a pipe, I'm gonna put an arrow that goes to that. So if the move includes the move, actually the move key of the move, continue. Oh, we are not handling the case when basically we don't have any more legal moves. Meh. Actually we are. We're gonna return positive infinity. Yep. And the total price will be positive infinity, and we're just gonna ignore it. And we're supposed to return the total price, the mean price actually. So yes, everything. If we somehow exclude all the moves and end up in a situation when we don't have any next moves, we're gonna return negative infinity. And what did happen? We didn't get an error of a maximum callstack, but I guess we still run into that. How is this not the same? Oh, yeah, I'm kinda stupid. Yep. We need to add our new move to the array of moves. So yeah, something is happening. We're moving it this way and that. Yeah, the B's are quite firmly on 0 and C is on 1, and we have a D on 3 and a 5 on B and a 7 on A, and we're doing a lot of things. Let's remove this and see if we get a result in some case. Yeah. Let's pause it here and spend 5-10 minutes waiting on this. So this thing didn't move a muscle in over 10 minutes, so of course I'm gonna terminate it, but let's debug it actually. Let's see what actually happens. What are the next moves? How are we moving? So we're getting all the next moves. Let's see what the first move is from A1 to 0. Yeah, of course. Moves is empty, so this doesn't include. Execute the move. We have our next burrow, and our next burrow has B at its move B from here to there. Is it complete? Of course it's not. Go one level down. So our burrow now is that one. What are the next moves? Where the next moves are from only from A1, A2. Yeah, we cannot move B. So we have, I guess, yeah, 25 possible moves. That's okay. So A2 to 1. Let's see if that is a valid thing. So our next burrow, and we have a terrible bug. We are comparing actually the burrow and not the next burrow. So this will never end, doesn't matter how much time we go. Okay, let's stop this. And let's restart it. Maybe we got lucky. We got unlucky that time. Oh. And let's run this. What is the next burrow? The next burrow is the one with B. What is the next burrow? The next burrow has B and A. Both of them are moved. It's not complete. Get the next burrow. So right now our burrow is one with the B and A. How many next moves we have? Well, technically we can move A back from 1 to A1, from A1 to A2. Why did we move that one? Oh, that was what is our example actually? BA. So that actually has no reason to move. Yeah, if we have an A character on A2, we don't need to move it. And if we have an A character on A1 and A2, we don't need to move it. So that's not a really valid move. Yeah, let's can move. Let's change it a bit. Are we moving to a side room? Are we moving to the corridor? So this is the this, and from of 1 is the side index. So if side room is equal to the pod to lowercase and side index equals 2, return false. Don't move the A. Actually, yeah, let's do this. If side index equals 2, then we're returning false because we definitely don't want to move it. And if the site index is 1, because it will be 1, we need to find pod. Actually, what is the, how did we call it, the burrow? Let's see what's on position burrow of side room 1 at position 1. That will be a pod. If that is equal to our own pod, then also return false. So if we have an A or AA situation, don't move them. Let's see how this runs. Did I remove? Yeah, I removed the breakpoints. That one and that one actually. So the next moves, 21 of them from A1, from B1, from C1, none of them from D, and that is wrong. We should be able to move D. Side room is D. So we have this situation. Side room is D and the pod is a D. So what is the burrow of D1? Oh no. Yeah, this is wrong. Because if the side index is 2, this means the side index is 1, so this will by definition always return false because we're checking the pod to itself. No, we need this case. Why did I remove the breakpoints again? Yeah, we have our nexts, yeah, 28 of them, because D can be moved. Run once more and we have the nexts, and there are only 19. We can move A1 to A2 to A1. Now we need that same code one more, because right now we're just gonna do an unnecessary move. If it's in A1, we don't want to move it. Actually, yeah. We can do this. Are we moving from a side room? Actually, this is better written. A, those can be A, B, C, D, and actually we can write all of them. A1, A2, B1, B2, C1, C2, B1, D2. So we can say, just say instead of this, we can just say if side room C includes from, and correspondingly here we can add side room includes 2. Yeah. So if we are moving from a side room, we might not want to move at all. Okay, get the next move. So now get the next moves. And we're only getting 19, so we can move from B1 or C1 or D1. And that is okay. So our current move is we're getting that we're moving from B1 to 1. Let's see how the next borough looks. So basically we move B and C, and we have empty A, empty A, empty D. Yeah, this looks okay. So what are the next moves? We cannot move the B, we cannot move the C, so we can move B2 or C1 or D1. And we're gonna say, okay, we're moving B1. The next borough is we move D on the third thing, and we have A here, which is okay, and we have B, and these are full. Okay. So we moved B. We're moving everything to the up and up. So how many moves? So now we're getting to a position where we have only 5 legal moves. And the first one is to move from 5 to B1. Yeah, let's see how that turns out. So our next borough, actually we removed the B that was here, and that B got here on a correct position. Of course it would have been better to be on B2, but let's leave it for now. That's not complete, so we're moving once more. So our borough is one with the B on B1. What are the next moves? We can actually move it back. We're gonna move it right back to 5. And we already have our moves. We have 5 to B1, and our next move is gonna be B1 5. Great. And we got our next borough, which is actually the same as the ones that we started. So now our next moves are these, from 5 to B1 first. That's the first option that we have. But that is already included in the list of moves, so we're gonna move the second thing. We're gonna move to B2, which is okay. And now that is fixed and that won't get to move. And our next borough, the move we made was basically take D1 over there. So to be honest, this looks kind of processing nicely. Ooh. And it says it managed to complete at something. And at 50, at 3000, something is off. Let's run this and see one of the completed thingies. So this is the next borough that we have. And actually looks completed. A, B, B, C, C, D, D. What are the moves we got to get to there. So our move is actually from 9 to A1. Let's see the array of moves. And let's actually try to paste this in Excel. So yeah, let's remove everything but the coloring. And let's see what we managed to actually do. This is the example. BACD CD BCDA. Take A1 to 0. Taken. Take B1 to 1. Taken. Take B2 to 3. To 3. Taken. Take C1 to 5. Taken. Take 5 to B1. And take B1 to 5. Actually copy paste. And take it to B2. Yes. That is the loop that we saw earlier. Just a second, is this thing recording? Yeah, it is. So that is done. We have an A and a B and a C. So D1, take it to 5. 1, 2, 3, 4, 5. D2, take it to 9. Take 5 to D1. Why? And take D1 to 7. And take 7 to D1. And take D1 to D2. Okay, took a lot of wrangling. Take 3 to D1. Take 1 to C1. And I guess I'm either missing a move. Yeah, the 15, trade 0 to B1. And the move that we are using to finish it actually is take 9 to A1. This thing finished. But the price is 8. Yeah, we managed to complete this at this price, and that is correct. So what is the total price is 58, and the min price is infinity, so the min price is 58 for this specific thing. And then we're just continuing. Yeah, and I will stop this because we'll get to run it now. Now it seems to be running. Just let's see if we get some outputs on the zeroed level. Not really. This is gonna take a while. And as we said, it's relatively hard to debug to deep recursion. So I can just say, no, this is kinda too slow. But what I will do, I will declare a cache, because this is one of the reasons that I didn't want to use incorporate, so to say, the moves, because doesn't matter how we got to a specific barrel, a single barrel will basically have a single solution, single best solution. So if cache of key, return cache of key. That's all there is. And just here we need to say cache of key equals price, and here we need to say cache of key equals min price. Let's see if this does anything. Well, it did in 3.5 seconds. So this was a total brute force when we basically didn't think. We just thought about what the moves are valid. You saw that the way that it actually moved, the moves were kinda haphazard. So it didn't make sense. It did solve it, but it didn't really make sense how it solved it. So now we have BC. The test example we're pronouncing correct, and now we have to have real input, and that's gonna be, so we have BC in A line, we have BA in B line, we have DA in C line, and DC in D line. Let's see how that runs. Yeah, usually the input will be much more complicated to solve. In the meantime, we're gonna try to see how we need to, because yeah, none of the things are where they should be. So what I would do, BCBA, so we have BCBA, DA, DC. So we very much want to minimize the movement of our D's, but we will have to move this one, and that's 2000. And then I would move this C over here. That's 1, 2, 3, 4, 500. And then we can do 3000. This thing finished in says 1067. And then we have 1, 2, 3, 4,000. And 200. We can move this here. 1, 2, 3, 40. And then we can move this out of the way. 1, 2, 300. and then we can move this here, and that's 1 2 3 4 5 6 7 8. We move this here for 20, we move this here for 1 2 3 4 5, and then we move this here for 30, this here for 300, this here for 1 2 3 4 5 600, and this here for 1 2 3 4 5 50. What's that sum? 11,053. So yeah, if the sum is less than 11,053, is more than 11,053, it's not good enough. This thing somehow managed to solve it for that many, and let's see if that is the correct number. Yay! Actually manual, and we are helping it once more. As you prepare to give the input your solution, you notice that the diagram they handled you was actually folded up. As you unfold it, you discovered an extra part of the diagram. Between the first and second lines of text that contain amphipod starting position, insert the following lines: DD, CB, BA, AC. So they want to be organized in a similar way. Aha. We're gonna have lots and lots and lots and lots and lots more moves. So basically what this means is that we have A1, A2, A3 and A4. It's quite okay. And this solution will work with one exception. This will need to be generated better. Yeah. Because I really don't want to type in a lot of A2s and A3s and A4s and B and C and D, because that will take a lot of typing. I was quite okay with this, but I'm definitely not okay with much more. So once I'm able to think how to check this thing, then we'll see. In the meantime, we have a relatively convoluted and very much unoptimized solution. Brute force, so to say. Get min price is kind of a brute force because we're not doing any kind of heuristics or A-star management, but it got the job done in something like 25 seconds. Yeah. So bye for now, and see you tomorrow for part 24.